Hello, everyone.
Yeah.
The title of my presentation is Generative AI, GIScience, and Disaster Management. Communities under a natural disaster are complex human environment systems. Under normal conditions, our communities have various interactions with natural and built environment. Suddenly, a disaster happens, disrupting these interactions and the normal life of people. Disaster management is an important research topic in GIScience. Very often, different types of geographic information are needed for disaster management. And a map uniquely links various types of disaster-related information through their location. When we talk about disaster management, we often talk about these four phases. So mitigation, way before a potential disaster, we may take measures to mitigate the potential impact of a disaster, such as strengthening our infrastructures. Preparedness, when we are expecting a potential disaster like a hurricane, we may take actions to prepare for this disaster, such as stocking up food and also boarding up windows. When the disaster happens, we get into the response phase, in which we try to rescue victims and reduce losses. Eventually, we get to the recovery phase, in which we repair damages and try to return to our normal life. Effort in all four phases is important for increasing disaster resilience. However, due to the unpredictable nature of disasters, the response phase often becomes the last and the most critical line for saving lives and reducing losses. There are some important information needs for disaster management and especially disaster response. When a disaster happens, we may ask questions like, where are the victims? Who need help and where? Where are the damages? Which areas are damaged by the disaster and which areas seem to be okay so far? Where are the potential future affected areas? If we are talking about a hurricane, which area may be affected by this hurricane in the next 1 or 2 days? Ideally, all information should be in near real time and have high spatial and temporal resolutions and meet our accuracy requirement. Meanwhile, we have also witnessed the faster development of generative AI, which refers to AI models that can generate new content, such as texts and images based on some input. Today's powerful generative AI models are often foundation models. They were trained on a large amount of unlabeled data and can be adapted to various downstream tasks. Some well-known generative AI models include ChatGPT, DALL-E, and also NASA and IBM's geospatial foundation model called PRISV, which was trained on a large number of satellite images. So if we put generative AI into this larger picture of GIScience and disaster management, from the left side, we can see we have different types of geospatial data, which we can leverage. So we have satellite and aerial image data, which capture different geographic features on the surface of the Earth. We also have data about weather, about climate. We also have data about anonymized mobile phone location data, which capture the mobility pattern of people during normal time and also how such mobility pattern change under a disaster context. We also have social media data, which provide information about what people were talking about and their sentiments under a disaster context. Then we have GIS and GeoAI methods, which also include generative AI methods. And very importantly, we need to have GIS experts experts like you in the audience who know how to use these methods properly. And we also need separate infrastructures to run these methods, especially when we are dealing with large geospatial data. Then we can contribute to various aspects in disaster management, such as finding victims, assessing damages, predicting future affected areas, and obtaining higher quality data. Ultimately, we want to contribute to disaster science and also inform decisions. We may want to understand more about the disaster impacts and how those impacts vary across communities. We may want to understand what are the socioeconomic and demographic factors associated with those impact disparities. We may want to better allocate our resources to increase community resilience and eventually achieve environmental justice. So in this presentation, I will share one study from my research group on using geo-knowledge to guide a type of generative AI, GPT models, for extracting location descriptions from disaster-related social media messages. Social media platforms such as Twitter, or nowadays also known as X, have been increasingly used by disaster victims to request help and share urgent information. So here we have two tweets from 2017 Hurricane Harvey. The first tweet says, #Hurricane Harvey, family needs rescue at this door number address. Too elderly, one is 90, not steady in her feet. The other one says, help, a pregnant lady is stuck in her car on I-45 between these two exits, #Harvey. If we can correctly and efficiently recognize these location descriptions, we may be able to help disaster responders reach victims more quickly and potentially save lives. Existing research on location extraction often used off-the-shelf named entity recognition tools, or NER tools. What an NER tool does is that it basically takes a piece of text as the input and outputs different types of entities. So if we have a sentence like donations to the Red Cross have provided help for people in Texas impacted by Hurricane Harvey, then an NER tool can tell us that Red Cross is an organization, Texas is a location, and Hurricane Harvey is an event. So we could just keep locations in the output and disregard other types of entities. So this approach can indeed extract some location descriptions, such as city names and also state names. However, it also has two major limitations. The first limitation is that the extracted results, they are separate entities, not complete location descriptions. So if we look at these two examples again, for the first example, this door number address will be extracted as three separate entities, Grant Street, Cypress, and Texas by an NER approach, instead of this complete door number address needed for geolocating the victim. Similarly, this highway segment will also be extracted as three separate entities instead of one complete address. This has a serious implication from a disaster response perspective, because if we mistakenly geolocate the victim to the center of the city of Cypress, or even to the center of Texas, we could waste very valuable rescue resources and time. Secondly, an NER approach is unable to identify categories or associated with location descriptions. And knowing the specific category of a location description, such as a door number address or a highway segment, can help us select the most suitable geolocating technique. Theoretically, both approaches, both limitations, they can be overcome if we create a new data set with complete location descriptions and also their categories labeled. And we can reuse such newly created data sets to retrain machine learning models. However, there is a lack of data sets labeled in this way. And creating such a data set can be time consuming and labor intensive. So with the emergence of generative AI and especially large language models, we thought about whether we could harness the power of these large language models for this task. We know that these large language models, they were pre-trained on large amount of data, and they can be adapted to a particular task through few-shot learning and sometimes even zero-shot learning. So it has the potential to help us overcome this difficulty of lacking properly labeled data. However, our preliminary experiments has shown that the default output of these large language models, they can be incorrect or inaccurate, possibly because they do not really understand the location descriptions that we need. So in this work, we propose geo-knowledge guided GPT models for location extraction. We propose to fuse geo-knowledge about location descriptions with a GPT model. And the result is a fused model that can take a piece of social media message and output, firstly, the complete location description, and then secondly, the category of this location description. So let's first look at the geo-knowledge part. For the geo-knowledge, in this work, we use the knowledge we derived from our previous research, in which we have identified 11 typical categories of location descriptions used by people during a natural disaster. Then we fuse this geo-knowledge with a GPT model. So the core idea is to embed this geo-knowledge in the prompt, which is a sequence of instruction to the GPT models. And we use examples to represent the geo-knowledge about the typical ways people describe locations. We have 11 categories, and we use 2 examples per category. And in each example, we provide one sentence, a sentence like Papa stranded in home, water rising above waist. And then we have this address here. We ask which part of the sentence represents location description, and we give a correct answer. So the location description and also its category. Then at the end of the prompt, we provide a new sentence, and we ask the GPT model to infer the location description and its category. And the model will basically look into the previous examples and try to get the answer. So this is our approach. How well does it perform? We evaluated using 1,000 tweets from Hurricane Harvey, which were manually labeled with the location descriptions and their categories. Because we have used 22 tweets in the prompt, we excluded them from the evaluation, and we use the remaining 978 tweets. For evaluation metrics, we use precision, recall, and F-score to align with the literature. For the test models, we use the default GPT models. So in different versions, we also use geo-knowledge guided GPT models. And we also include fine-tuned BERT and different versions of typical NER models. So here are our results. So firstly, we can look at the performance of these models without differentiating specific categories. So in this table, in this area, we have the performance of typical NER models. And then here we have the performance of the GPT models without the guidance of geo knowledge. And then here we have our geo knowledge guided GPT models. So compared with typical NER approaches, our geo knowledge guided GPT models show about 40% better performance. And then compared with the default GPT models, we find that the geo knowledge guided GPT model show a performance of about 76% better, demonstrating the importance of having having geo knowledge to guide the behavior of large AI models. Just having these large AI models is not enough. Next, we can look into the performance of these models across different categories of location descriptions. So in these three figures, we have precision, recall, and F-score. And the horizontal axis, we have the 11 categories of location descriptions, and each color of the bar represents one model. So overall, we can see that geo knowledge guided GPT-3, 3.5, and 4 overall perform better than the two other models, suggesting that if we use the same geo knowledge to guide different versions of GPT models, newer versions do perform better than the older versions. While geo-knowledge guided GPT-4 performs reasonably well in most categories, its performance is still limited in some categories, such as Category 4, highway exits, Category 10, adjacent geographic areas, and also Category 11, road segments, suggesting there is still room for further improvement. So conclusions for this case study: messages posted on social media platforms during natural disasters often contain important location descriptions about victims and accidents. Typical NER approaches cannot effectively extract complete location descriptions and their categories. In this work, we propose geo-knowledge guided GPT models, which use geo-knowledge to guide the output behavior of GPT models. And this approach achieves a performance about 40% better than default NER tools and about 76% better than default GPT models without the guidance of geo knowledge. And the extracted location descriptions, they can help disaster responders reach victims more quickly and potentially save lives. So I have shared one application of generative AI in disaster management. There are other possible applications. So we can use generative AI to map disaster damages. We can estimate the areas burned by a wildfire through remote sensing image, identify buildings damaged by an earthquake, assessing flood depths, and so forth. My colleague, Dr. Wenwen Li from Arizona State University, has some very nice work on assessing the ability of the NASA IBM Foundation model PRISV in flood mapping. So you can also check it out. We can also predict future affected areas. If we are talking about a wildfire, where will the current wildfire spread? We can also use generative AI to increase information quality if we are interested in using wind speed data. But currently, we only have the data in a spatial resolution of 9 kilometers. Can we increase it to a resolution of 1 kilometer? We can even use it for community engagement. For example, we could show the residents of a neighborhood how this neighborhood may look like if it is affected by 1 meter of flood water. So a summary for this presentation: communities under natural disasters are complex human environment systems. GIScience plays an important role in disaster management. Generative AI and Geo AI provide new tools for studying disasters and increasing community resilience. In this presentation, I shared some existing and possible applications, such as identifying victims, mapping damages, predicting future affected areas, increasing data quality, and community engagement. There are some important considerations when we use generative AI in disaster management. Firstly, quality. We may want to think about, does generative AI extract the right information that we need? Sensitivity. Does the output of generative AI vary substantially if we slightly change the input? So evaluations on the output of generative AI will be highly important to ensure that it indeed plays a positive role in disaster management. That is all. Thank you very much.